Hey, my name is Costas Maranas. I'm a professor in the Department of Chemical Engineering at Penn State. And what we do in our group is that we're trying to use computations to try to understand biological systems at different scales, both at the network end with metabolic networks, how those are put together and why, with different living systems, and also at the protein end of things, trying to understand how enzymatic catalysis evolved and how we can tweak enzymatic catalysis to achieve different goals. This is a very active area of research. There's a number of people in our community that are contributing along this line of achieving goals relevant to patient outcomes. People are developing metabolic models that tend to be patient-specific. They capture the genotype of individuals, and based on that, we can make suggestions as far as dietary modifications, so they can minimize the risk for different disease, or for identifying ways to cure ailments that they may already have by modifying diet. Things have advanced dramatically over the last 4 or 5 years. Right now we have detailed human metabolic reconstructions that allow us to pose those questions that we couldn't pose them 5 or 10 years ago. At the same time, computational power is increasing, and our facility with those models and our ability to use them correctly is also increasing. So some of the pitfalls and dangers of using those models, I think the community is becoming much more aware of, and they're much more adept at using them. There are challenges at all levels. At the modeling level is detail. You need to try to capture as much as you can about metabolism, because it's complicated. It's not going from a single microbe to a multicellular organism that changes as a function of time, and it's spatially distributed, poses unique challenges in trying to make predictions. So just because you know what an enzyme does, that's not enough. You need to know where this enzyme is present, in what tissues, and when is it expressed under what conditions. So it becomes a multi-dimensional challenge. And addressing all those questions, you will have to rely upon a larger and larger continuum of experimental techniques to be integrated. Something that I've learned the hard way over the last 10, 20 years. Never fall in love with your models or your algorithms, because sooner or later somebody will poke holes in both of them. So use models as a way of extracting information and forming as a vehicle that allow you to think about a particular system. Don't think of models as the ultimate truth. And also use algorithms as the same way that experimentalists use a microscope or surgeons use a scalpel. Use algorithms to investigate what the model is trying to tell you, and whether what it's trying to tell you captures reality or not.